Hello and welcome. My name is Shepard Moore, and I'm a postmaster student in Chemistry Division in the Physical Chemistry and Applied Spectroscopy group, and I'll be presenting the project on behalf of my mentors Laura Lilly, Lorene Stromberg, and PI Harshini Mukundan, titled Sabotaging Iron Metabolism. How can we use siderophores as radiotherapeutics against emerging pathogenic threats? To start, I'd like to talk about some current strategies and challenges that face the field of targeted alpha therapy. As we can see illustrated, infected tissues will be targeted by the therapeutic to specific surface proteins or antigens. Once bound, the radioisotope will have a more localized path of radiation, and the decay of the alpha emitter will breach the membrane of the bacterium, causing cell death. There are distinct advantages from each component of this strategy. This includes targeting, antibody highly specific for target organism, reducing off-target biological effects. Our linker, it determines pharmacokinetic behavior and radiochemical dose. Chelate, fast binding kinetics, and favorable thermodynamic properties to mitigate free metal ion release. And lastly, antibodies have multiple epitope binding to one singular antigen, mitigating bacterial resistance. Unfortunately, there are some limitations. Antibody targets are limited to the surface of bacteria. Pathogenic strains have multiple virulence factors, thus multiple methods for evading host immune systems. Protein targets are readily mutated, creating resistance, and intracellular infections, which is inside the host cell, cannot be targeted with antibodies. Our group decided to address these limitations while boosting the advantages by taking interest in siderophores. A siderophore is a compound that has a high affinity for iron and transports it to the microorganisms, such as bacteria and fungi, for fundamental biological processes. Bacteria are dependent on iron for their metabolisms, and they secrete this molecule in low iron concentration environments to acquire more. Extracellular iron ions typically have a +3 charge, but once taken in through bacterial transporter proteins to the cytoplasm, they are reduced to +2, allowing the metabolism to actually use it. The constant tug of war of iron between host cells and pathogens brings siderophores at the head of the table. Host cells use lactoferrin proteins to bind iron for their own metabolisms. A transmetallation reaction can occur, causing the bacterial siderophore to steal the captured iron for their own metabolism. But host cells have a way to steal back the stolen iron by sequestering the siderophores and lipocalin-2 proteins. This causes the bacteria to produce new stealth siderophore that will bind iron undetected from lipocalin-2 proteins. So, this displays the great need for iron in bacteria, and we want to take advantage of that by replacing iron with a radioactive isotope, using a Trojan horse method of delivery inside the pathogen. One major bacteria that we wanted to treat with radioactive siderophores was Pseudomonas aeruginosa. It is an extremely antibiotic-resistant bacteria where infection typically originates from hospital environments. Let's say you are going to the hospital, you're transported there, and then you're admitted for your condition. There's a 1 in 5 chance that you will be exposed to Pseudomonas. An estimated 32,600 infections per year. And from those infections, an estimated 2,700 people die per year. Our goal is to reduce these numbers to the best of our capabilities. Here's a short list of Pseudomonas targeting siderophores that have the potential to bind thorium-227 instead of iron. Thorium-227 is a radioactive molecule. The three siderophores of interest are dysferrioxamine, enterobactin, and pyoverdine. Next, we wanted to examine the ability of Pseudomonas to take our thorium-conjugated siderophore in bulk. We labeled the radioactive siderophore with a fluorescence reporter, FITSI, and took various fluorescent microscopic pictures demonstrating successful uptake into the bacteria. As you can see in panel A, it is just the FITSI. In panel B, DFO and FITSI, C, iron, DFO, and FITSI, and finally our thorium-conjugated siderophore, which you can see is being uptaken into some of the bacteria. To have a comparative baseline between siderophores and antibodies, we checked the antibody cross-reactivity against 3 strains of Pseudomonas. Anti-Pseudomonas antibody DOTA conjugates were produced by means of the reaction on the right. High percentages of thorium were detected, which provides great confidence because typically labeled thorium is only at 70 to 80%. As you can see highlighted in the red, one of our strains, 39257 DOTA, was used for future studies. To show the biocidal efficacy of radioactive siderophores to typical targeted alpha therapy antibodies, we compared the growth rate constants on a specific strain of Pseudomonas, BAA47. As it can be seen in the figure, 1 microgram of antibody DOTA plus 1 microcurie of thorium-227 has the lowest growth rate compared to the DFO complexes at different concentrations of thorium, 1 and 0.1 microcurie respectively. For our controls, 1 microgram of pure antibody and 0.5 millimolar DFO with iron and untreated bacteria were used. In conclusion, some goals that we reached were producing anti-Pseudomonas antibody DOTA complexes, also achieving MIC curves of siderophores and common antibiotics, including 3 strains of Pseudomonas and other reference strains. Lastly, conjugating confirming that our siderophores bind thorium-4 and can be uptaken in bulk. Some future goals that we continue to press towards are completing thorium-227 radio-labeled experiments with a full suite of reference strains. And finally, examining cytotoxicity to human cells in mixed cultured models. I hope you enjoyed our project presentation, and thank you so much for your time.